This video is a discussion of slides 49 through 66 of Chapter 1. Its main focus is resonance structures. Resonance structures describe the electronic distribution within a molecule. Some molecules actually have valid Lewis structures which display formal charges on two different atoms or on multiple atoms. For example, if I look here at ethanoic acetate, I have a resonance structure which has a negative charge on the oxygen up at the top, but I could draw a completely valid Lewis acid structure where that negative charge is on the oxygen down at the bottom. And when we draw resonance structures, we typically draw a double-ended arrow between this, and this is unique to resonance. So both of these structures are valid Lewis structures for the same molecule, and we call those resonance structures. Think of these resonance structures as a snapshot of the different electronic distributions that together contribute to the overall electronic nature of a molecule. We can think of it as being sort of like this drawing over here on the left and sort of like this drawing here over on the right. Whenever we draw a resonance structure, I could also draw it as a resonance hybrid, meaning I put the electrons in this dashed line here with the negative sign still here for charge, and just realizing that that negative charge is distributed between this oxygen and that oxygen. When we go through organic chemistry, we're going to find out if we can ever draw a valid resonance structure for a molecule, we think of that as a stabilizing feature. So if I look at ethyl acetate by itself, just one drawing here, I say, oh, that's not very stable because I don't have two bonds to oxygen, but I can draw another resonance structure where I have a negative charge down here, and because I can draw a resonance structure, this is actually a stable species. Let's now draw some more resonance structures. First of all, let's take out this first molecule which has 2 hydrogens, 1 carbon, and 3 oxygens. I put together some scenarios and do some trial and error, and I finally come up with a molecular structure where I have a complete octet around every single atom and 2 electrons around hydrogen. And that's a valid material. Are there any resonance structures for this molecule? Not that I can draw, okay? If I look at the second molecule down here, I notice it looks very similar to the first one, but I'm missing a hydrogen, okay? And so I have to come up with a way of putting all the electrons around there and still having my octets around carbon and oxygen. And one valid way to draw that is to put a negative charge down on one of the oxygens. And I can quickly see that I have 2 equivalent looking oxygens here, so I could draw another resonance structure for that. And in fact, I'm also going to draw the hybrid structure for that. Okay? Again, if I can draw a resonance structure of a molecule, I think stability. Now let's look down at this molecule with 2 carbons, 4 oxygens, 4 hydrogens, and 2 oxygens. I come up with a valid way of drawing it. It turns out it's ethanoic acid. And if I look at that, is there any other valid resonance structures that I could draw? No. This molecule is fine the way it is. Each of the carbons and each of the oxygens has a complete octet around it. There are no negative charges, so it is, quote, a happy molecule. If I pull off a hydrogen off ethanoic acid, I would think that would be less stable. However, I can draw a resonance structure of this molecule down here because I have 2 equivalent oxygens, and I draw a valid resonance structure, and I also can draw a hybrid resonance structure. This species, even though it's charged, has some stability because it's resonance stabilized. The interconversion between these 2 species, the 2 resonance structures, is depicted by using curved arrows. Those curved arrows represent the movement of electrons. And let me draw a few in here. So if I take the electrons that are in oxygen, notice I haven't drawn the lone pairs. But we know they're there. We know there's 3 lone pairs of electrons up there. I move 2 of those electrons down between the carbon and oxygen to form a double bond. If I form a double bond here, I've got 5 bonds now to carbon, and that's very, very unstable. And so I need to move electrons out of the way again to the oxygen, and I come up with this resonance structure. Now this arrow in between means they're interconverting back and forth, so I can use curved arrows again to represent the right-hand side molecule being converted back into the left-hand side molecule. I'm just going to draw electrons again and move them around. Every time I draw an arrow, that represents the movement of 2 electrons. That arrow has to have 2 barbs on it, so each barb represents an electron. Whenever I represent moving electrons, I need to start that arrow at electrons. I'm either going to start it at electrons, which is at these lone pair over here, or as we're going to see in the future, I could start them at a pi bonding electrons. I could literally start them at a double bond here and move them out to oxygen. The end of the arrow always has to end either at an atom, at a sigma bond, so here my electrons end up at a sigma bond, or they must end up at a pi bond. Again, that's going to be coming up in a later chapter. The idea of resonance is one of those central themes for organic chemistry because it predicts stability. It predicts that I can pull a hydrogen off of this carboxylic acid and it's a stable species. Let's look at a few rules that are not resonance structures. For example, if I look at this molecule on the left-hand side, I see that I have a positive charge on that. Well, could I draw a resonance structure? For example, if I were to just move these 2 electrons over to that sigma bond, that would stabilize that positive charge. However, I literally broke a single bond here. That breaks that's a rule. I can never break a single bond. So this is not a resonance structure. This is actually chemistry, okay? Another example down here on the bottom is let's move this hydrogen atom over to the positive charge and let's move its electrons with it. That just puts the positive charge on the second atom. Well, that sounds all right. However, I've broke this single bond right here between the carbon and hydrogen, and I moved it over to here. So that's not a resonance structure. This is chemistry again. This is a chemical reaction. Another rule is that we do not exceed an octet for second row elements, meaning carbon, oxygen, and nitrogen, and the halogens. And so let's see here. Here I have an ionic species, an anion. I'm going to draw those electrons, starting at the electrons, moving down to a sigma bond. I get this structure right here. However, how many bonds do I have to carbon here? I have an octet, and I cannot exceed the octet for second row elements. So this is also not a resonance structure. This is not valid for resonance stability. I actually have too many electrons around carbon. Let's look at a few more. This time I'm going to sort of do it real quickly. Here I have a double bond, so I can start at pi electrons. I move them over to sigma electrons. Now I've got too many bonds at carbon, so I got to move some out of that double bond over to oxygen, and I get this structure. And if I went the reverse direction, move the electrons back down. I got too many bonds to carbon, move the electrons back to the pi bond here. Yeah. That's a valid resonance structure. If I look at this second set of molecules down here, I'm also going to start at the pi electrons, but I'm going to go to down to the below now and move the double bond down here. But I can't move anything out of the way now. Okay, I end up with a positive charge up here at this atom because I moved electrons away from it, and I end with a negative charge down there. There's an easy way to look at that. So this is not resonance. In fact, in my product here, you see that I only have, in this case, I only have 3 bonds to carbon. I have my 4 here because there's also a hydrogen here that I'm not showing. But I have 5 bonds to carbon down here because originally there were 2 hydrogens sticking down here because I start off with 4 bonds to carbon. So I have 5 bonds to carbon, so this is not a valid resonance structure. So if I have 2 resonance structures, which one is more stable? Which one is more important? Which one is the more prevalent structure? So here are some rules for determining which of the resonance structures is most important. The most important resonance structure should have the greatest number of atoms in a molecule that fulfill the octet rule. Number 2, atoms prefer to fill their octets with bonding electrons rather than non-bonding electrons. So if I have bonds to my atoms, that's more significant than having non-bonding electrons. If I do have a formal charge that is present, either a plus or a minus, the negative charges are always more stable when they're located on a more electronegative atom. For example, fluorine's more electronegative than oxygen, oxygen's more electronegative than nitrogen, and nitrogen's more electronegative than carbon. If I have a positive charge, a cation, they can be located on electronegative atoms, but only if their octet is filled. If opposite formal charges are present, like I have a plus and a minus, there should be as little charge separation as possible. So let's look at this molecule down here. If I look at this molecule, my octets are fulfilled. I got 8 electrons around oxygen because I have 2 lone pairs up here. I got 2 bonds to oxygen, 4 bonds to carbon. I got 4 bonds to carbon because I have a hydrogen sticking out here, and I have a hydrogen sticking out here. If I draw the resonance structure where I move the electrons from the double bond to create a new double bond and push the electrons in the double bond between carbon and an oxygen out to the oxygen, I notice I still have octets in all these atoms. I now have 3 lone pairs or 6 electrons in one bond, and so forth. Okay. What I don't have here, though, is that I have charge separation. Okay. And so this one here actually has charge separation and is not as stable. This is the major resonance structure for this pair of resonance structures. Let's also look at some examples now. And I got a bunch of them coming up here because this is an important concept in organic chemistry. Here's a pair of resonance structures. I can interconvert them by moving electrons from the double bond up to the oxygen. Or if I want to convert in the other direction, I move those electrons back down to form a double bond. In both cases, the electron octets are fulfilled. I got 8 electrons around oxygen. I get 8 electrons around carbon. Here I still have 8 electrons around oxygen. 1, 2, 3, 4, 5, 6, 7, 8. How about down here? Do I have? No. I do not have 8 electrons around carbon. So in this case, this is my major species, my major contributor, and this is my minor species. Okay. Here's another example where I have 2 resonance structures that are interconverting. Here this happens to be an anion, and I could draw resonance structures where I move some of the electrons from the lone pairs to form a triple bond. That forces some electrons off of carbon, because otherwise I'd have 5 bonds, over to oxygen, and I form this new species. I could interconvert back by moving those electrons back down to between oxygen and carbon, which forces those electrons back to nitrogen. Let's look at these molecules and see how are their octets full here. So if I look at oxygen, it has a full octet. If I look at carbon, it has a full octet. If I look at nitrogen, full octet. The same thing's true over here. I have octets. But in this case, what I have is and let's count lone pairs too. I have 1, 2, 3, 4 sets of lone pairs. 1, 2, 3, 4 sets of lone pairs. Let's go down to number 3. And let's see. I have a negative charge here on oxygen, and I have a negative charge here on nitrogen. Therefore, my oxygen is more electronegative. This is going to be my major species. When both resonance forms obey the octet rule, the major component is the one with the negative charge on the most electronegative atom. Another example. Here is a neutral species. I've drawn two different resonance structures. I'm going to interconvert them. I'm going to move electrons from my lone pair down between nitrogen, and I'm going to move those electrons over to oxygen. I could interconvert back by moving those electrons back down, which pushes those off because I have too many bonds to nitrogen then. Okay. And let's see, do they all fulfill the octet? Okay. I got 8 electrons around oxygen. I got 8 electrons around nitrogen. I got 8 electrons around oxygen. And the same thing's true over here. So those are fine. Let's count up lone pairs. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Now let's see. I have a negative on oxygen. That's fine. And I have a positive on oxygen. That's sort of fine too. But how about the smallest charge separation? It turns out no charge means there's no separation. So that, in fact, would mean that that's my major component. So the octet rule is fulfilled on all atoms. However, if I have a resonance structure drawn with no formal charges, it will be the major contributor to that resonance properties. Another example. Here is a molecule which has 6 carbon atoms represented by these angles here. I have 3 double bonds and I have 6 hydrogens. That can interconvert to this resonance structure. Notice all I'm doing here is I'm drawing the double bond on the right top side here, and I'm drawing the bond on the left top side here, and the same thing here. I've just rotated all the double bonds around. I can draw arrows to represent that. If I push these electrons over here, I need to push them over off of this one, which then forces them back off to this one, and I get this new structure. And here's a set of arrows showing how they interconvert back. In fact, these two structures are the same. So there is no major contributor. They're both major contributors. And we like to draw these sometimes as organic chemists as resonance hybrids, where I just draw the electrons in a dashed line or a solid line here, because I don't exactly know where the electrons are. They're somewhere here in the middle. I know there's 1, 2, 3, 4, 5, 6 in these double bonds. This dashed line represents those 6 electrons, and this whole line represents those 6 electrons. This is a very common drawing for this molecule. This molecule is called benzene, and we'll learn about that shortly. Let's actually draw the resonance structure, then indicate which structures are major and which structures are minor. So I put my thinking hat on and I start organizing electrons and atoms to try to come up with a reasonable structure. And the first one I came up with is that I have CH3, which is represented up here. I have an oxygen bound to carbon, and then I put the 2 hydrogens on there. Notice I don't have 4 bonds to carbon here, so that's where I put my positive charge. If I want to draw a resonance structure, I'm going to move electrons down, and when I do that, I form this structure, and now my positive charge is on oxygen. Let's see, this one does not have an octet in it, where this one does, so this one happens to be the major component. This one has an incomplete octet on carbon, this one has a complete octet on carbon, but it also has a positive charge on oxygen. Let's now draw the resonance structures for the following compound. It's an anion because it's a negatively charged. I'm again going to put my thinking hat on and try to put together a reasonable structure for that one. I have CH2, which is represented here, a carbon with an oxygen attached to it, and that carbon also has a CH2 attached to it. I'm going to put my negative charge, and I'll put it on carbon because it looks strange, okay? It has too many electrons here. And when I draw a resonance structure, I can move electrons around to form a double bond between the 2 carbons, and that pushes the electrons off carbon because I have too many bonds, then I have 5, pushes them onto oxygen, and I have a reasonable resonance structure. If we were to look at which one would be major, I notice that I'd rather have the negative charge on oxygen rather than on carbon. So this one is the major product right here. This one has an octet around it, this has an octet, this has an octet. Same thing here. They all have octets, but in this case, the negative charge is more stable when it's on oxygen. I could also draw these same drawings doing line angle drawings, meaning I'm going to leave off all the non-essential hydrogens that show up on carbon, and it simplifies it a lot. I have to remember, though, that if I have a negative charge on the end of a line angle drawing where carbon is, there are implied 2 hydrogens there. If I have a double bond where carbon is implied, there are 2 hydrogens there. There's also 3 hydrogens out on this carbon, and there are 3 hydrogens out on this carbon. Let's draw some arrows in there, just like we drew up above. I move the electrons down to form a double bond. I move the electrons out to push them onto oxygen. To interconvert back to the original structure, I move those electrons back down to form a double bond, and I push those out to be negative. Okay. Notice here I haven't even drawn the lone pairs of electrons anywhere. So this one's a little harder to visualize because I don't have those lone pairs of electrons. Seeing that lone pair of electrons there is very beneficial for this type of resonance structure. One more example here. Let's put on our thinking caps. Let's draw a reasonable structure for this molecule. I have a CH3, nitrogen, carbon, oxygen. I'm going to fulfill my octets. I have to use some double bonds to do that. 8 electrons around oxygen, 8 electrons around carbon, 8 electrons around nitrogen, 8 electrons around carbon. Each of my hydrogens has 2 electrons around it. Can I draw a resonance structure for that? Well, let's just grab some electrons and start pushing them. So if I push those electrons to form a triple bond between nitrogen and carbon, I have 5 bonds to carbon, so I need to push some electrons back out onto oxygen, and I form this resonance structure. Let's see if I have octets around this one. Let's see, I got 8 electrons around here, 8 electrons, 8 electrons. That looks pretty good, okay? And I can interconvert, okay? I'm going to move some electrons back to interconvert to those. If I looked at the stability of these two ones, there is charge separation here, and I have a negative charge on oxygen. This one's going to be more stable because that's got full octets and no charge separation. Let's push electrons a different way. In this case, let's just pick these electrons out here and push them over to that double bond right there. And if I push them there, I need to move electrons off of that double bond and push them over to nitrogen. And what I form is a positive charge on oxygen now and a negative charge on nitrogen. Okay. In this case, I still have charge separation, but I have a negative charge on nitrogen. So this species in the middle here is more stable than this one. And this one here is less stable than this one because oxygen is more stable with a negative charge than it is with a positive charge. Okay. And let's push some electrons to interconvert these. So I'm going to move those electrons back down to form a double bond, which forces the electrons back over to oxygen. Okay. There are some more resonance structures I can draw. Let's now grab some of the electrons between the atoms. So I'm going to take some of these electrons that form the double bond between carbon and oxygen and push them out to oxygen. Notice I don't push any other electrons away because I'm moving only toward oxygen. Now, if I look at this molecule, I have 8 electrons around oxygen. I only have 6 electrons around carbon. So I have not fulfilled the octet. So that's an unstable species and a very small contributor to resonance structures. Let's push the electrons back. I'm going to draw one more place I can get electrons, and that's between the double bond between nitrogen and carbon. So this time I'm going to push them over to nitrogen, okay? And when I do that, I literally form a negative charge on nitrogen. Again, what we see is that I don't have an octet around carbon because I only have 6 electrons now that are being shared. So it's an incomplete octet. There's charge separation and nitrogen. So if I looked at all these species and tried to decide which one is the most stable, the first thing I see is that this central atom molecule is more stable than any of them. So that's my number 1 stability. And then these two over here, they have an incomplete octet, so I know those got to be 4 and 5 stability. Now I need to decide between these two species. It's more favorable to have the negative charge on oxygen, so that's number 2, that's number 3. I come over here, my negative charge is on oxygen on the top one, so that's 4. And here my negative charge is on nitrogen. That is the least stable of any of these resonance structures. Sometimes resonance structures cannot be adequately represented by a single Lewis structure, so we draw resonance structures, but we can just draw a hybrid resonance of those two resonance structures by sort of distributing that charge and those electrons between the atoms. So here I have electrons that are extra on nitrogen, and if I draw a resonance structure, I move those electrons down between the carbons and I get an octet now around this carbon, and I can interconvert back by moving those electrons back over to nitrogen. So this one would be the most stable resonance structure because my octet is fulfilled around carbon. But I could draw a resonance structure. Notice there is a positive charge on this, so it's a cation, and part of that positive charge is on carbon, and part of that positive charge is on nitrogen. It's a resonance hybrid. And my electrons can often be described as delocalized. They're between two different atoms. They're delocalized between those two atoms. Let's look at that stabilizing effect of delocalization. If I take acetic acid, which is a weak acid, and throw it in water, water can act as a base and actually pick off that hydrogen. What's left is this acetate anion, and I know that if I look at it, I can move those electrons down here and push those electrons out here and draw a resonance structure. This is a stabilizing effect because my anion is actually stabilized because I can draw a resonance structure. That implies that acetic acid is a pretty good acid compared to other organic compounds because my resulting conjugate base is actually stabilized by resonance. You can sort of think of those electrons between the two oxygens here as sort of a 1.5 bond. They're just delocalized. Scientists have shown that the negative charge is on either one of those oxygens and that they're interconverting. They did some isotope experiments which were pretty fancy just to prove that. And finally, that was the end of the resonance structure. I want to go through one more exercise here that's kind of non-related before we go on to the next set of slides. This is actually calculating molecular formula from experimental data. Let's say I have a colorless liquid that has a composition of 84.1% carbon and 15.9% hydrogen. I do some very sophisticated math techniques and stuff forth to get that information. I then also put my original molecule in a mass spectrometer and found out that my molecule has a molecular weight of 114.2 grams per mole. I want to know what the molecular formula for that molecule is. People used to do this type of experiment all the time in the early 1900s before they had either sophisticated instrumentation or before they knew some of the models about organic chemistry. So let's take them, and here's the sort of the scenario how we're going to go. We're going to take the mass percentages, which are 84.1% carbon and 15.5% hydrogen. We're going to convert those to mole percent because that tells me how many atoms I have in my compound. and then I'm going to form the mole ratio to form the empirical formula, the simplest number of carbons and hydrogens. I'm going to then form the empirical mass. I'm going to do a little bit more math to it and come up with the molecular formula. Let's walk through this example. So let's calculate the mole percents from the mass percents. Mole percents from the mass percents. Let's just assume I have 100 grams of this that I isolated. That makes the math a little bit easier just because when you do percentages, this percentage plus that percentage always has to add up to 100. So let's just pretend like it's 100 grams. So here I go. I have 84.1 grams of gram percents of carbon, and I have 15.9 gram percent of hydrogen for 100 grams total. I then divide by the molecular weight for each of those different elements, 12.01 for carbon and 1.008 for hydrogen. That converts it over to a mole percent. Okay. Now that I have mole percents, I could draw a molecular formula because moles tells me the number of atoms. I literally would have C7 and 15.8 hydrogens. We now need to get the simplest common denominator. So what I'm going to do now is I'm literally going to divide each of those by 7 to get the simplest molecular formula possible to get it into a ratio. I take the smallest whole number, divide each of them by 7. I get 1 over 2.26. I've never seen a formula with a 2 1/4 hydrogens here, so I know that's not right. I know that's about a quarter. So if I multiply everything by 4, that'll bring that up to a whole number. So I literally multiply both of these subscripts by 4 to get C4H9. And that is my empirical formula now that is corrected to bring that to the lowest common denominator. I then need to compare that to the actual mass that I measured in my mass spectrometer. So let's find out what the mass of this molecule is. The molecular weight. I know I have 4 carbons. Each of those has a molecular weight of 12 grams per mole. I have 9 hydrogens. Each of those has 1 gram per mole. So I add those up and I get 48 plus 9 gives me 57 grams per mole. I remember that I measured 114.2, so this cannot be the correct molecular formula yet. I need to do a little bit more math, and so I take my actual molecular weight as measured by mass spectrometer. I divide that by my calculated molecular weight based on my percentages, and I get 2. And then all I have to do is multiply everything by 2. So I'm going to take carbon C4H9, multiply that by 2. And my molecular formula now is C8H8. And that has a molecular weight of 114.2. And the carbons and the hydrogens are all in the correct mass percentages.